Hello, this is Professor Arai in section 6.1 Single Proportion. Before I start, I need to note that chapter 6 includes many new formulas, so make sure you are taking notes while listening. Chapter 6 revisits many concepts we learned in chapter 3, 4, and 5, and it focuses on a measurement each time. So for 6.1, we will revisit many concepts we learned about single proportion. We will talk about the confidence interval, sample size, the shape of the distribution, and the hypothesis test. So, first, confidence interval for single proportion. Last time we stopped at this formula. We said if we want to find the confidence interval for single proportion, the formula we used was statistic plus or minus Z star times SE. We said that the statistic, which is the proportion, was the part over whole. The Z star were fixed values according to the confidence interval. If you remember, for 95% confidence interval, the Z star was 1.96 and so on, times the SE. Now, this is a new formula, so make sure you write it down. If you are doing confidence interval for single proportion, the standard error has a new formula, and this is equal to the square root of p hat times 1 minus p hat all over sample size. So instead of going into Bootstrap and creating and generating many samples, now we have a formula and we can find it right away. So make sure you're writing this down. If the sample size is large enough, where n times p hat is larger or equal to 10, and n times 1 minus p hat is larger or equal to 10, then the confidence interval can be found by this formula. P hat plus or minus Z star times the SE. The SE is the square root of p hat times 1 minus p hat over n. So let's revisit an example we finished section 5.2 with, the syntaxes example. This example said that in March 2011, a random sample of 1,000 US adults were asked, do you favor or oppose sin taxes on soda and junk food? 320 adults responded in favor of sin taxes. Give the 95% confidence interval for the proportion of all US adults that favor these sin taxes. So what do we have? We have the 1,000. This represents the n, the sample size. We have this number, 320. 320 divided by 1,000 gives me the p hat. We also now know that since we are looking at the 95 confidence interval, then the Z star is 1.96. We have all the information. We can go ahead and apply the formula right away. So before we start applying the formula, we need to check that the criteria is matching. The criteria said that we can use the formula if n times p hat is larger than 10. And this is obviously clear to us since n is 1,000. Now, as I said, this Z star for the 95% confidence interval is 1.96. This is the formula. You plug in the values. So one more time, p hat is the 320 divided by 1,000 plus or minus the Z star for the 95 times the SE. And we can find that the interval is between these two numbers. This was the exact answer that we got when we used the Bootstrap. And we can say that we are 95% confident that between 29.1% and 34.9% of US adults favor sin taxes on soda and junk food. These were the values when we did the bootstrapping. Example 2. In a random sample of 500 US citizens, 280 plan to vote in the upcoming election. We plan to construct a 90% confidence interval for the proportion of US citizens who plan to vote. What is the sample proportion? Sample proportion is the p hat. The p-hat can be found by 280 divided by 500. And if we do that, we will get the sample proportion to be 0.56. Next question, what is the z-star? Now, since we are talking about the 90% confidence interval, the z-star is 1.645. You either have it in your notes or you memorize it, or if you don't have it, you can always find it on StatKey. So I'm going to show you how. Let's say you forgot what is the z-star that belongs to 90% confidence interval. What you need to do is you would go to StatKey, go to normal, keep it 0 and 1, click to tail, and enter the percentage of the confidence interval, 0.90. Once you do that, these values down there are the z-star. So the z-star will be 1.645. And that was our answer for B. C, what is the standard error? Now, since we have more than 10 for n times p, we can use the formula. And the formula is the square root of p hat 1 minus p hat over n. You plug in everything and you will get SE, or the standard error, to be 0.0222. Now, the second concept in this section is the margin of error. In the confidence interval, this was the new formula that we just saw. In the old formula, we had the confidence interval is statistic plus or minus margin error. If you compare the new formula to the old formula, we can see that the margin of error is this side over here. So write this one down. Margin of error is equal to the z-star times SE. Now, the third concept in this section is determining the sample size. Before you do any experiment, you need to know how many samples or how many cases you need to sample in your collection. So to know which n you need to collect, you need to apply a formula. This is the formula that you need to know if you want to find the sample size. And it is quite complicated, but it is basically worked out. If you look at the SE formula, you can work it backward until you get the n by itself. However, in most cases, we don't know the p-hat. We don't know the proportion, because the proportion is the part over whole. So if we don't know the whole, we cannot actually use this formula. And that's why for the 95 confidence interval, assuming the z-star is 2, we can use this more generic formula. So in most examples, we will use this formula. However, if you have the p-hat, you will use the blue formula. So make sure you write both of them down. Let's see example 3. In a random sample of 500 US citizens, 280 plan to vote in the upcoming election. We plan to construct a 90% confidence interval for the proportion of US citizens who plan to vote. We found from example 2 that the standard error was 0.0222. What is the margin of error? So we just saw that the margin of error is actually z-star times SE. The z-star for 90% from the StatKey is 1.645. The SE is given. You multiply both of them and you get the margin of error to be D, 0.0365. Example 4. Suppose we want to estimate a sample size with a margin of error. So suppose you are starting an experiment and they told you that they want their results to be with a 3% of margin of error. Since you know the ME, you can estimate the N, which is the sample size, how many cases you need to go and collect. So we know that the formula is M equals 1 over ME squared. So I know the ME. ME is 3% or it's 0.03. So you plug in 1 over 0.03 squared and you will get about 1000. So the actual answer, or the approximated answer, is 1111. but from the choices, it will be closest to 1000. Now, after talking about the confidence interval, we will move to the second part of this section, which is what is the distribution? How is it going to look like? So this is very important. If the normal distribution has a sample size that if you multiply it with the proportion will give you number bigger than 10, and so this both of them needs to happen, and n times the parenthesis 1 minus p larger than 10, then I can look at the single proportion distribution as a normal distribution, meaning I can write it down as n parenthesis sample statistic. Instead of sample statistic, I'm writing the population because I'm thinking of it as a huge, big distribution, comma, the standard error. So the standard error this time will be the square root of p times 1 minus p over n. So notice how we are not using p hat, we're using the p. And this only can be done if the n is sufficiently large. So the sample size is really big. Example 5. The 2010 census reports that of all the nation's occupied housing units, 65.1% are owned by occupants. SE is 0.048. If we were to take random samples of 100 homes, what would be the distribution of p hat? So every time they ask you about the distribution, they're not asking you about the confidence interval or the hypothesis test. They are looking for one single answer. How would you describe this distribution? And as we've said, the distribution for a large sample size will look like a normal distribution. So if you look at the sample size, this is 100 times the p is obviously larger than 10, and 100 times 1 minus p will also be larger than 10. So I can look at this distribution as a normal distribution. So if I look at my options, these are the options. So I know this is going to look like a normal distribution. It will be centered around the proportion, and in this case it is p, which is 0.651. It will have the standard error that is SE. So this would be my distribution. And again, this is how we worked it out. We know that the sample size is 100. We know the proportion is 0.65, so NP is larger than 10, and n times 1 minus p is also larger than 10. Once you have the two criteria, then you can use the normal distribution property by saying this is a normal distribution centered around the mean, and its standard deviation is equal to the standard error. Okay, let's look at example 6. From 2010 US Census, we learned that 14.6% of the residents of Oregon speak language other than English at home. If we take random samples of size n equals 100 and calculate the proportion of sample that speaks language other than English at home, describe the shape, the mean, and standard error of the distribution. So again, the distribution, describing the distribution, meaning you need to write it in the n normal distribution form. So what you will do is you will take the n times p. P in this case is 0.4146. This is obviously larger than 10. And n times 1 minus p is also larger than 10. Since it is large enough, this distribution will be a bell-shaped, meaning it will be a normal shape with a mean of the population, which is 0.146, and standard error of the formula. So you will apply the formula, which is p times 1 minus p over n. So you have the standard error to be 0.035. So you can write this distribution in this sentence. So what would the distribution look like? It will be a normal distribution with a mean of 0.146 and standard deviation as 0.035. Part B, describe the shape, the mean, the standard error of the distribution of a sample proportion if we instead take random samples of size 500. So let's see what's going to happen if the size is 500. So one more time, n times p is larger than 10, and n times p minus 1 is also, I'm sorry, n times 1 minus p is larger than 10. So since n is large enough, this would be a normal distribution. The mean of this normal distribution is at the p, which is 0.146. The standard error, on the other hand, you need to apply the formula. So the SE is going to be the p times 1 minus p over n. This time the n is 500, and you notice that the SE, or the standard error, became smaller. So previously, when n was 100, the standard error was 0.035. In part B, when n was 500, the standard error was 0.016. So you can conclude the large sample size doesn't affect the shape or the center. So this is still a bell-shaped and is still centered around 0.146. However, it will reduce the standard error. So the larger the sample size, the smaller the standard error. Last portion of this section is the hypothesis testing. So the hypothesis testing is always centered around the null. And because it's centered around the null, the formula for the standard error will be different. So if you are doing a problem that deals with confidence interval, you have to use SE equals square root of p hat times 1 minus p hat over n. However, if you're doing a problem that deals with hypothesis testing or finding an evidence, then your SE formula will become this one. Notice how instead of the p hat, now I'm using p0, which is the value of the null hypothesis. So make sure you distinguish between the two standard error. Make sure you write them down so you know which one to use when the question is presented. The other part that we talked about in chapter 5 is the Z, or the test for the single proportion. So last time we said that the Z is equal to statistic minus the null over SE. And we used the Z every time we talked about the standard normal distribution. Now the statistic is p hat. The null is p0. The SE is the new formula. So the new formula for Z looks a little bit more complicated, but it really didn't change. So it's statistic minus the null over the SE when you are doing testing. And we also have two criteria that we need to follow. We need to have the n times p0 this time needs to be larger than 10, and n times 1 minus p0 needs to be larger than 10. And if this happens, then we can find the p-value using the standard normal distribution. So let's see an example. Example 7. Of the 2,430 Major League Baseball games played in 2009, the home team won in 54.9% of the games. If we consider 2009 as a representative sample of all the MLB games, is this evidence, so again, focus on the word evidence, of a home field advantage in Major League Baseball? Basically, they're asking, if you are playing in your state, would you have a higher chance of winning? So since I need to prove something or find evidence, that means I need to do the whole hypothesis test. First, you need to check if your counts are greater than 10, and in this case, they are. Then you need to write the hypothesis test. So the null is saying that the p is equal to 0.5. Now, where did we bring this from? So we're saying either they have a better chance, that means they are winning more than half of the times, or it's 50-50, whether you play in your hometown or not, it's going to be 50-50 chance. And that's where the 0.5 is coming from the 50-50 chance. So the null will be p equals 0.5. And the alternative is saying p is larger. That means you have a higher chance of winning. And then the next step is finding the z. So the z is the p hat which is the sample statistic, which they gave me, minus the null over the SE. You plug everything in and you get the Z. Once you have the Z, you can find the p-value using StatKey. So you keep the standard normal distribution. This is a right tail, and you enter the Z here. So adjust your cutoff to 4.86. And once you do that, you will find the p-value to be a very small number. This is e to the -7. It means it is out of 7 decimal places. So this is a very small p. So notice how my p changes each time because it's generating new samples. But in both cases, my p is so small, beyond the 5%, beyond the 1%. This is a huge evidence. Any team that plays in their hometown has a better chance of winning. So we do have strong evidence of a home field advantage in Major League Baseball. Last example, example 8. In a random sample of 500 US citizens, 280 plan to vote. So notice this is the same problem coming up again and again. But let's see what is different in this example. We want to test to see if this provides evidence that the proportion of US citizens who plan to vote is greater than half. So again, the minute they say test or evidence, we need to perform the hypothesis test. Hypothesis test meaning I need to find the hypothesis null and alternative. I need to find the Z, and then I need to find the p-value. So before I do any of this, I need to make sure that my values are higher than 10, and I can see that this is higher than 10. Now, part A is saying, is this a right tail, left tail, or two tail test? So looking at the sentence, it says it's trying to prove that the citizen who plan to vote is greater than half. Since I'm saying greater, then this is a right tail test. Part B is asking me to find the standard error. Now remember, since I'm finding the standard error for something that I need to test, then I'm using this formula. So I have to use the null in this case. P0 is half. And N is this number here. This is the total number in my sample. This is just the proportion. So N is 500, P0 is half. You plug in these values in there and you'll get the standard error to be 0.2236. Part C is asking me to find the test statistic. So if you don't remember, test statistic is the Z value. So one more time, the Z is the proportion minus the P0 over the standard error. Proportion is the part over whole. So 280 divided by 500. And this will be 0.56 minus the null proportion over the SE, and you'll get Z to be 2.683. Once you have the Z, you need to go to StatKey to find the p-value. So let's do this. This is a right tail test. Z is 2.683. And once you change your Z's, you can see the p-value over here. So the p-value is 0.0036. And this is exactly what I found last time. So I have the p-value. And the last part of this question is saying, what is the conclusion at 5% level? So you compare your p-value to the 5%. Obviously, the p-value is way smaller than the 5%. That means we reject the null and conclude that more than half of US citizens plan to vote. Do the same. Vote. Anyway, this is the end of 6.1. Make sure you write all these formulas, and please try these examples by yourself after listening to this recorded lecture. That's it. Take care. Thank you.